Welcome to the Explainer. If you're a focused learner looking to master the actual tools that keep our electrical systems safe, well, you're in the exact right place. Today, we're talking about incredibly high stakes. We're talking about preventing catastrophic equipment failure, stopping fires way before they even have a chance to start, and mastering a tool that's an absolute powerhouse for electrical safety. I'm talking, of course, about the Megometer. You probably just call it the Megger.
Okay, let's just dive right into our roadmap for today. Think of this as your essential safety briefing. We're going to cover the insulation leak problem, crucial pre-test safety measures, setting leads and test voltages, running the actual test, and then, finally, interpreting your readings.
All right, Section 1, the insulation leak problem. Before we can actually test anything, we've got to know what we're fighting against, right? Look, electrical insulation degrades over time. It just does. It gets attacked by heat, moisture, dust, and just plain old age. And these faults, they act exactly like pinhole leaks in a high-pressure water pipe. But instead of water dripping behind your drywall, you've got invisible electrical leakage escaping. This stray electricity is exactly what causes sudden equipment failure, incredibly dangerous shocks, and potentially devastating fires. It's a completely invisible threat, which is exactly why we need a specialized tool to hunt it down.
Now you might be wondering, hey, why not just use my standard multimeter to check the wires? Well, a standard multimeter uses a very low voltage to measure low resistance. It's kind of like gently pouring water down a pipe to see if it's clear. But a megometer, that applies high DC voltage. We're talking anywhere from 250 volts all the way up to a massive 5,000 volts. This massive electrical pressure actively pushes current through the system to expose those hidden high-resistance weaknesses that a normal everyday multimeter would completely miss.
Moving right along to Section 2, crucial pre-test safety measures.
Okay, lean in and listen up closely here, because this is, without a doubt, the single most critical part of this entire explainer. We are dealing with intentionally generated, extremely high voltage. So, strict safety protocols, they aren't optional. You absolutely must isolate and discharge your circuit completely before you begin. Step 1, you turn off the main power supply, period. Step 2, disconnect any sensitive electronics. Step 3, discharge any capacitors in the system using a shorting wire. I honestly cannot stress this rule enough. You must never, ever, ever connect a Megger to a live, energized circuit.
And before you prep the tool itself, like if you're using an X-Tech model 380260 or something similar, before you plug anything into those V, ohm, and COM input terminals, you have to inspect your actual gear. Your test leads and alligator clips have to be in absolutely perfect working order. They must be clean, and the insulation literally cannot be broken or cracked anywhere. Because if your leads are compromised, you're not just risking damaging the equipment, you are risking giving yourself a massive, severe electrical shock.
So, before you move forward with any of your connections, this is your magic number: 0 volts. The circuit must read exactly 0 volts. It needs to be completely de-energized before you even think about touching it with your testing leads. If your meter detects AC voltage on the line, it's going to give you a constant warning beep. If you hear that beeping, you stop immediately. Okay, safe and sound. Section 3, setting leads and test voltages. Assuming we've fully secured the area, let's methodically walk through how you physically wire up your meter for a successful test. For all measurements on these meters, you're going to connect your red test lead right to the V-ohm input terminal, and your black test lead goes to the COM terminal. Now, when you take those leads over to the equipment you're testing, you connect your line terminal, which is your red lead, directly to the conductor itself. Then connect the earth terminal, that's the black lead, straight to the ground. Actually, if you happen to be testing an industrial motor, that black ground lead just connects right to the grounded metallic motor frame. Next up, you have to select the correct test voltage on the meter, and you have to precisely match this test voltage to your specific application. So for low-level control circuits or just your standard home wiring, you're only going to use 250 volts. But if you're checking heavy industrial motors, you're going to dial that up to somewhere between 500 and 1,000 volts. And for those really heavy-duty, high-voltage cables, you're looking at injecting 2.5 kilovolts or even more. But please, I need you to burn this massive warning into your memory right now. Applying 1,000 volts of direct current to the wrong thing will instantly and permanently destroy sensitive modern components. I'm talking about entirely destroying power factor correction capacitors, melting electronic light dimmers, and completely frying everyday household items, routers, flat-screen TVs, you name it. You always have to verify you've matched the test voltage to the equipment's actual rating and make absolutely sure those sensitive devices are fully disconnected before you ever press test. All right, Section 4, running the insulation test. Let's see how this all builds together. This is where the rubber finally meets the road, and we gather our data. When you look at the interface on these meters, it's pretty straightforward. Down at the bottom, you usually have a rotary switch to set your desired megaohm test voltage. Right in the center is that all-important test button. And usually, just above it is a lock function. Now that lock is a fantastic little feature for hands-free operation. By pressing test and lock at the same time, the meter will continuously run the high voltage test, just beeping every couple of seconds so you don't have to awkwardly hold the button down yourself. So, here is your exact firing sequence. First, set your rotary switch to your desired voltage position. Second, press and hold the test button. When you do that, you're going to see a flashing high voltage symbol pop up on the screen, and you'll see the actual test voltage being pushed right into the wire. Third, and this is key, when your reading is complete, you keep the leads firmly connected to the wire and then release the test button. This lets the circuit safely discharge itself back through the meter. Seriously, do not remove those leads until the display safely returns all the way back to 0 volts. So how long do you actually hold that test button down for? 10 to 60. You generally need to hold the button for 10 to 60 seconds, especially on highly capacitive devices or really long cable runs. It simply takes time for the instrument to apply the high DC voltage properly and for the resistance reading on the screen to finally stabilize. So just be patient. Let the meter do its work so you get a truly accurate reading. Now let's think about a common scenario, testing high voltage cables. When you're checking the insulation resistance between cable conductors, you have to remember to completely disconnect the opposite end of the cable first. If you leave that other end connected to the grid, you are going to get massive errors from electricity leaking into other equipment further down the line. It'll completely ruin your test results. And finally, Section 5, interpreting resistance test readings. So what do these numbers actually mean for you?
You've safely run the test, you've got a number stabilized on the screen. What's it telling you? Well, a reading of over 100 megaohms, that means your insulation is excellent. 10 to 100 is good, totally healthy wire. 1 to 10 megaohms is a serious warning sign that degradation is actively happening right now. And anything under 1 megaohm indicates a dangerous, catastrophic failure that has to be addressed immediately. Oh, and by the way, a lot of meters max out at around 2,000 megaohms. If your insulation is perfectly healthy and exceeds that, the screen might just display a 1. That's a good thing. It's just letting you know the resistance is extremely high and the wire is incredibly safe.
Let's anchor all this data in a real-world example, okay? Say you're testing an industrial motor. You disconnect it, you connect your line to the terminal, and your earth to the grounded motor housing. You apply 500 volts for 30 seconds. If the meter spits out 50 megaohms, congratulations, you've got a healthy motor. But if it reads 0.5 megaohms, you are looking at imminent motor failure. That 0.5 reading demands immediate action to stop incredibly expensive destruction before you ever try to restart that machinery. Before we wrap up today, I really want to share a quick pro tip to elevate your diagnostic skills over time. It's called the Polarization Index, or PI test. This is a real pro-level technique where you measure resistance at the 1-minute mark and then again at the 10-minute mark. If the resistance reading is steadily climbing and increasing over that time, it means your insulation is dry and healthy. But if the resistance stays completely flat and low across those full 10 minutes, it's a huge red flag indicating you've got moisture or contamination trapped inside your system. Ultimately, a megaohmmeter is designed to answer one highly critical question. Is your electricity leaking right now? Regular preventative testing prevents fires, it protects incredibly expensive equipment, and it ensures the absolute safety of everyone in the building. So I'm going to leave you with this provocative thought. Considering the invisible threats lurking in aging wires, when was the last time you confidently checked the safety of your own electrical systems? Thanks for joining me for this explainer. Stay safe out there, and I'll catch you next time.